so you guys did this lab where you dropped the picket fence through the photo gate and you measured the acceleration due to gravity. And give or take some experimental error, it was probably really, really close to 9.8 meters per second per second. That's the accepted value for the acceleration due to gravity on Earth. It varies a little bit with where you're at and how high above Earth you are, but for things near the surface of Earth and without air resistance, everything, regardless of size, regardless of weight, falls at the same or falls with the same acceleration. They all fall with an acceleration of 9.8 meters per second per second. Okay? So in the problems we do, we're considering only free fall cases, and that means we're ignoring air resistance, we're ignoring any other external forces. We let something go, it's going to accelerate towards the surface of Earth at 9.8 meters per second per second. Okay? Unless we're on a different planet, and then we'll tell you what G is. Okay? So this first problem we're going to work, just to make sure everybody's on the same page here. A person drops a penny from a tower that is 200 meters tall. We're supposed to figure out two things: how long it takes the penny to reach the ground, which is a time, and the penny's velocity the instant it reaches the ground. So how fast is it going when it smashes into the ground? Okay, a lot of times people want to say 0. Well, it's on the ground, it's at rest. But we're not interested in after it hits the ground and comes to a stop. We're interested in how fast it actually hits the ground, right? When you drop something on your foot, it doesn't hit you at rest. It comes to a rest after it runs into your foot. Okay? So we're starting these problems the same way every time. What do we know? Maybe a picture. Okay, so I guess I'm going to start with the picture. My building is 200 meters tall, measured from the ground. So my ground is 0 meters. The top of my building is 200 meters. And since that's positive, I guess up is positive. So down would be negative. All right. So how long does it take the penny to hit the ground? So let's list what we know. I know where it starts. Its initial position is 200 meters up. I know where it ends. Its final position is 0 meters. Do I know anything else?
Well, that's all the problem gives you, but we can also calculate our displacement from what you got here.
Negative 200 meters, which makes sense because it didn't fall up, it fell down. Okay? And it says a person drops a penny.
Okay, if you drop something, you're not throwing it, so your initial velocity is just 0.
Right? It started at rest, 0 meters per second.
And we do know acceleration due to gravity.
Right? And we know the acceleration is actually the acceleration due to gravity, which is 9.8 meters per second.
But again, we have to pay attention to sign. So if up is positive, down is negative, then gravity acts down.
Yeah, so negative 9.8 meters per second per second.
Okay, so we don't know how long it takes the penny to reach the ground.
And we don't know its final velocity. So we're looking for time and we're looking for final velocity.
It really doesn't matter which one we do first.
Okay, so let's see. My first equation has time. Well, let's just list them. V equals V naught plus AT. Does this one help me?
It turns out it doesn't really, because I have two unknowns. I don't know the final velocity and I don't know the time. So let's go to our second equation. Change in position equals 1/2 AT squared plus V naught T. Now I could use this equation because I know everything but time, but if I do, it's going to end up being a quadratic equation. So we're going to hold.
And then there's the last equation, which says final velocity squared equals initial velocity squared plus 2 times the acceleration times the change in position.
And this one could work if we wanted to solve for the final velocity, because we do know the rest of the information. So I guess we can take our pick.
I think I'm going to start with the final velocity, because if I use this one to find time, well, actually, this one will be okay too, because that initial velocity is 0, so it would drop out, and I wouldn't have to use the quadratic. Sometimes you have an option of using the quadratic equation or not, and I'm going to try to skip it for now. So I'm actually going to find the final velocity first. I'm going to start with the second part of this problem. So our final velocity is unknown, so v squared. Our initial velocity is 0. Our acceleration is plus 2 times negative 9.8 meters per second squared.
Times negative 200 meters, because that's our displacement. And then we're going to do a little bit of simplification, and we get v squared equals
3920
meters, except negative times negative. Okay, it is positive, which is good, and this is meters squared per second squared. It's good that it's positive, because I'm going to have to take a square root to answer this, and I can't take the square root of a negative.
That'd be
so
imaginary.
v equals, and it's a square root, so plus or minus
62.61.
62.61 meters per second.
Now, in math, we would just call it good and circle it, but in physics, we want to know which one it is, because it's only one of those velocities.
Right? It's falling down. It's not falling up, so it's a negative.
It's the negative answer.
62.61 meters per second.
All right, we got the last question answered.
And the last question, so now we're going to go back to the first one. How long does this take?
Now, we could technically use the first equation if we want, because now that we know the final velocity, it might just be easier to just use the first equation.
62.61 meters per second. So I can say V equals V naught plus AT. So negative 62.61 meters per second equals 0 minus plus a negative, right? 9.8 times T. So divide both sides by negative 9.8. And
I got 6.39 seconds.
6.39 seconds.
It's positive, that's good.
All right, can't go backwards in time.
Yep, so a couple ways you know if you messed up your sign is if you get a negative answer here.
If you're trying to take the square root of negative, you did something wrong.
And if you get a negative time, that could indicate you got a sign goofy.
Okay. Now, pretty straightforward problem. A couple things to keep in mind. If you're dropping something, that means its initial velocity is at rest. And when something hits the ground, its final velocity is not 0. Its final velocity is 0 after it hits the ground, not when it hits the ground.
Okay. Next problem says a person tosses a volleyball upward from a height of 1.5 meters, so it has an initial velocity of 6 meters per second. Let's go ahead and draw a picture. Here you are. And a height of 1.5 meters. And I'm going to call this positive and down here negative. So up is positive for this problem.
In the positive direction.
Okay, let's start listing what we know. From a height, so y initial is 1.5 meters, positive, and initial velocity.
This one was tossed, right? It was thrown, so its initial velocity isn't 0. It's actually 6 meters per second.
It and throwing it up. Okay, so 6 meters per second.
We know its acceleration.
Okay, A is
negative 9.8.
9.8.
Just because we threw something doesn't mean gravity stops pulling on it.
Right. Anytime something is affected by gravity, we're going to use that number.
Okay, and we're supposed to figure out...
Okay, let's look at what we need to figure out. How long does it take the ball to reach the top of its flight? So to go from here to here, what else do we need? How long does it take the ball to reach the ground? So I'm assuming that's from here to here.
Yep, time of flight.
What is the velocity of the ball just before it reaches the ground?
Okay, so there's a lot of information here. I think we can do A. It's actually pretty straightforward. There's a hidden piece of information in A. Okay, it says how long does it take the ball to reach the top of its flight? Okay, and there's something kind of special about the top of a trajectory of a ball's motion, because when you throw something up, it slows down the entire time it's moving up, and then it stops
for just an instant,
right?
And then
changes direction and falls back down.
Happily, we are concerned with that
instant at the top. So we actually know its final velocity is 0. Now, you've got to be clear on this. This is not the final velocity when it smashes into the ground.
Right.
This is the final velocity at the top of the flight, because it's not going up anymore. It hasn't started to fall back down. Its instantaneous velocity at the top is 0. Okay? So we can use that piece of information to find the time for just the upward part of the trip. It's not anything with the downward part.
And this looks pretty simple because I can use all this information here, here, and here, and first kinematic equation.
G equals V naught plus AT.
V equals V naught plus AT. So
0
equals my initial velocity was 6 plus negative 9.8 times, lost my units, times time.
T in seconds. All right, so negative 6 equals negative 9.8 meters per second. So negative 6 divided by negative 9.8 is 0.61 seconds.
Okay, that seems like it makes sense.
Yep, a little bit more than half a second for it to slow down and stop.
Okay, so you got that one answered.
Okay, now B says how long does it take the ball to reach the ground?
So we'd be going from here clear to here.
Right, so from the beginning of the problem to the end of the problem, and we know its final position there is 0.
Okay, so if we did that, we know delta y, the final position is 0. Minus the initial position, 1.5 meters, so delta y
is negative 1.5.
That might come in handy, let's see.
Okay. Now, we know its initial velocity, we know its change in position, we know the acceleration. We could use the second kinematic equation here, but we're going to end up with a quadratic.
Okay.
Now, I don't have a problem with that, but it's a little bit more complex. However, if we knew how fast it was going when it hit the ground, then we wouldn't have to use the quadratic equation. Okay?
So that final velocity, not this final velocity, because we're looking at right when it hits the ground.
Right when it hits the ground. So we want a final velocity, and we know a displacement, we know an acceleration. We can use the third kinematic equation because we know the initial velocity. So v squared equals v naught squared plus 2 times the acceleration times the change in position.
Okay.
So v is unknown.
Is the initial was at 6?
6
Plus 2
times negative 9.8 times negative 1.5. Okay? So 6 squared is 36.
Okay, 36 plus all
And
that
then
stuff.
2 times 9.8 times 1.5. And those two negatives add up to make a positive, or multiply to make a positive. So 29.4 plus 36 is 65.4. Then if we square root that,
We get 8.1 meters per second. But again, we have to think about, what do we mean? Do we mean positive or do we mean negative 8.1 meters per second? And because the ball is actually falling back down, we know it's a negative 8.1 meters per second.
Now we know the initial velocity.
We know the initial velocity is 6. We know the final velocity for the whole trip is negative 8.1. We know the acceleration.
So looks like the first equation will be
The
nice.
first equation should work excellent for this. So negative 8.1 v
8.1
equals v naught 6 plus negative 9.8 a times t, which we don't know. So let's see, negative 8.1
minus 6
minus 6 is negative 14.1 divided by negative 9.8 is 1.44 seconds.
So t is back here. You're right, 1.44.
1.44 seconds.
Okay, let's see. Think about if this answer would make sense.
Okay,
It
well,
took
it took
0.61
0.6
to go to
seconds
the top.
to get to the top, and if we doubled that, it would be 1.2 seconds to get back to where it
There
was,
to there,
and then it's got to fall just a
bit
little bit
more.
further. So yeah, it
So
makes
yeah,
sense.
1.44
And that last
makes
part of
perfect
that
sense.
trip is where it's going to be moving the fastest, so it should take the least amount of time.
All right.
Right.
So don't feel like you have to do A, B, and C in the order that they give you or that we give you. You might skip around because it might be easier
It
to
might
do
be
something
easier to-
out of order.
Out of order, and if you don't mind using the quadratic,
Yeah,
use
you
the
can use the
quadratic.
quadratic, especially if you've got the program or the calculator to do that.
Yeah. Okay. All right. So this last problem is a little bit tricky. A passenger rising in a hot air balloon moving up at 5 meters per second drops his phone.
Oops.
Whoops.
If it takes 8 seconds for the phone to smash into the ground, how high was he when he dropped the phone? And how high is he when the phone hits the ground? So he's going to keep moving even after he drops the phone. So we'll start with a picture. Here's my hot air balloon. Okay, and let's see. It's moving up at, I just drew through that, 5 meters per second.
I guess I just
So is that gonna
decided
be positive?
up is positive.
The
I
gr-
don't
down
know
is
how
negative.
high it is. Whatever this distance is, I don't know it. But I do know the ground is at 0.
Okay.
Okay.
Took 8 seconds.
And I know a time. All right. So my initial velocity, because the person's moving up when he drops the phone is also moving up. So my initial velocity is 5 meters per second, and it's positive.
And it's not just 0 because he's not dropping it from rest. Since he's
Right.
going
Right.
up,
Since he's in motion with the phone
The
phone
phone's
is
going
in
up with
motion. So initial velocity is his velocity, 5 meters per second. It is up. Final position, y, is 0 meters. The acceleration due to gravity is negative 9.8 meters per second, and time is 8 seconds.
and we are looking for, I guess, displacement. So
And yeah, we want to know his initial position. How high was he when he dropped it? So delta y equals negative 9.8 times a half.
negative 4.9.
4.9, right? Times 8 squared plus v naught 5 times 8. So delta y equals 64 times 4.9 plus 40. And this is negative, right?
I got negative 273.6.
Negative 273.6 meters. Now, this delta y tells me that the phone fell negative 273.6 meters. But then I know it must have started 273.6 meters high. Okay,
So sign mattered.
sign mattered. The initial position is a positive 273.6 meters. Now, the second part of this problem is a little bit tricky. Okay, how high is the person when the phone hits the ground? Okay, which means I've got to do two things. Okay? I've got to figure out, okay, how far he moved in the 8 seconds the phone fell and add that to his initial height. Okay? So while the phone was falling, it went up and came back down. This guy just continued to move up.
Okay, so he was still going up for 8 seconds.
So he was still going up for those 8 seconds. So in those 8 seconds, how far did he go? Well, it's the second kinematic equation, but there's no acceleration. So change in position equals 1/2 at squared plus v naught t, but there is no acceleration. He's moving up at a constant rate. So his change in position equals v, 5, times t, 8, which equals 40 meters. So he managed to go another 40 meters while the phone fell to the ground. So if he was at 273.6 when he dropped it, and now he's another 40 meters higher, his 273.6 plus 40 is 313.6 meters above the ground.
That wasn't so bad.
Wasn't so bad. Okay. A lot of times you can divide a problem up into 2 time intervals to help you out if you need.